In this video, I'm going to do a quadratics example that has to do with projectile motion. So I think this is some of the, the more fun and interesting applications of quadratics. And so hopefully you'll enjoy this too. So with this function, so we have this function h of t equals negative 16t squared plus v sub 0 t plus h sub 0. Now, if you're looking at that thinking, oh, that doesn't look fun, it looks really complicated. Well, let me break it down. So v sub 0, or v naught sometimes it's called, is initial velocity. So this is going to just turn into a number. So this is initial velocity, and that just talks about how fast something is moving. And then h sub 0 right here is just the initial height. Okay, so this is a general equation that we can use for projectile motion. And so now let's get to the actual problem. So let's say we have a bowling ball launched upward from the top of a 230-foot building. So imagine for a second, so we have this building, it's 230 feet tall, and then you have a bowling ball on the top of it, and it's going to be launched upward. Well, what happens when things are launched upwards? They eventually are going to go down and they are going to hit the ground. So that's the general, movement, the shape of the movement. And you can see it looks like that motion looks like the shape of a parabola, part of it. I mean, obviously the bowling ball kind of cuts off the left side, but it looks very parabolic in how it's moving. And so this ball has initial velocity of 60 feet per second. And we'll be using the following steps. We're going to find the maximum height of the ball, how long it takes to reach the ground. So let's start with the equation. So we talked about v sub 0 is initial velocity. So we're told in the problem that that's 60 feet per second. So I'm just going to write v sub 0 initial velocity is 60 feet per second. So when you have these kinds of problems, you want to just kind of look in the problem, figure out, well, what is that initial velocity? Write it down. And then what is the initial height? Well, the ball is starting 230 feet off the ground, so we're going to say it's 230 feet. Okay, so then we can take those numbers and plug them into the formula where they go. So above here, we talked earlier about how v sub 0, that's initial velocity, that's before the t. So I'm just going to put 60 before the t, and I'm going to put 230 at the end because the height goes at the end. And so now we have our equation, like our completed equation. The beginning equation was sort of the shell that you use, or the template that you use for projectile motion, but we have a completed equation with our exact numbers from our problem. So part B asks, describe the plausible domain. So plausible means like makes sense or reasonable. Domain, remember, is usually x, or the independent variable. In our case, it's t, which is time. So if time is starting when the ball is being released or projected into the air, I think we got to just ask ourselves, well, what numbers make sense for t? Well, it makes sense to look at when t is 0, like the ball is just sitting there when time has started, until, the time that the ball hits the ground. So until the time when the ball hits the ground. It doesn't make sense to look at negative time. It really doesn't make sense to look at time beyond, when the ball hits the ground, because who cares? The ball's already on the ground. So, so 0 until the ball hits the ground. We don't know when that time is, but we're going to find it in a minute. Part C, this parabola will open up or down because of A. So now we can look at our picture, forget the equation for a minute. We can look at our picture and see that it's going to open down just because of the nature of what would happen if we threw a ball up in the air. But if we also look at our equation, A is negative. So A is negative 16, which is a negative number. And because it's negative, that parabola is going to be facing down. So we can use the equation to confirm that it would face down. And then part D asks us to find the Y-intercept. So, the Y-intercept, is probably, right here, but we'll graph this later on where we don't graph the building in there. But let's just think about the steps of finding the Y-intercept. So to find the Y-intercept, what we have to do is we have to plug 0 in for x, or 0 in for t. So if we plug 0 in for t, I'm just going to do that right here. We get negative 16 times 0 squared plus 60 times 0 plus 230. So those terms with 0 in them, those just end up being 0, and we end up getting 230. So the y-intercept is 0, 230, and it represents the starting height. So when we think about it, we can sort of look at our picture, and if we think about, where the building is as our y-axis, and we think about the ground as our x-axis, then you can see that the bowling alley starts out at 0, 230. But we also were able to do it algebraically to confirm that. And then for E, we're wanting to find the vertex. So that's an important part. That's that peak point or that max point of how high the ball gets in the air. So the vertex is representative of, a number that might be helpful in terms of the situation to know. So, so this is our peak height. So let's find the vertex. So we're going to use the formula, which normally starts with x, but I'm going to write t since t is really like our x in this problem. So the formula is x equals, or t equals, negative b over 2a. So we're going to find our b value. So that's 60. So negative 60 divided by 2 times a, and when I'm telling you, or when I'm saying b is 60, it's because it's this number in front of the t variable. A is the number in front of the t squared. So 2 times negative 16. Okay, I can put that in my calculator. I can do negative 60 divided by 2 times negative 16. You can also use your fraction button if you want. And I end up getting t equals 1.875. Okay, and so that's the x value or the t value of the vertex. So the vertex is 1.875. Okay, so that's like this number right here is 1.875 on that t-axis or x-axis. And then to find the height, all I have to do is plug that into the equation. So I'm going to do negative 16 times 1.875 squared plus 60 times 1.875 plus 230. So I plug it in to find that y value, or in this case, the h value, the height. So negative 16 times 1.875 parenthesis squared plus, I'm just going to plug this all in one step, plus 230. And hit enter, and I get 286.25. And so this is the height. So that is how tall. So the ball starts at 230 feet, it gets thrown up in the air, and the very peak is 286.25 feet. So 286.25 feet. So if you're ever asked in a problem to find the max height or the lowest height, whatever, if the parabola was facing the other direction, it'd be the lowest value. That's really a key, like a clue that you have to find the vertex. So usually finding the vertex in quadratic story problems is important. It usually gives you, information that you're being asked. So this is the vertex, and it represents the peak height of the bowling ball. Okay, and so now we're going to find the x-intercepts. Okay, so let's go find the x-intercepts. So if we think about, our picture up here at the bowling ball, the x-intercepts would be like here and here. This is also like, I could write the t-intercepts because x and t are really interchangeable here. We're using t for x. So in order to find the t-intercepts, we're going to use the quadratic formula. So we're going to say t equals negative b plus or minus the square root b squared minus 4ac all over 2 times a. So my b value is 60, so negative 60 plus or minus 60 squared minus 4. My a value is negative 16. My c is 230, all divided by 2 times negative 16. Make sure when you divide, you're dividing everything, like including that negative 60. Okay, and so we're going to go ahead and we're going to simplify. Let's simplify underneath the square root. So we have 60 squared minus 4 times negative 16 times 230. Okay, so that's underneath our square root. So I'm going to come down here. I get negative 60 plus or minus the square root of 18,320 all over 2 times negative 16 is negative 32. Okay, So now at this point, we're going to do two equations. I'm guessing that we can't, that's not going to be a nice number, but maybe. Let's see. If we take the square root of that, we get a decimal. So it's up to you whether or not you want to write that whole decimal out. I'm going to just leave it like with the square root since it's a long decimal and I don't have to write it all out if I use the square root symbol. So I'm going to say negative 60, and I'm going to use the plus sign, the square root of 18,320 divided by negative 32, and then I'm going to do it again, negative 60, only I'm going to do minus the square root 18,320 divided by negative 32. So I've got two equations there, so I'm going to put them in my calculator one at a time. So negative 60, and actually, you know what, let me use parentheses. Well, no, we'll do the top like this. Let's do it this way. Negative 60 plus the square root of 18,320, enter. Notice I'm hitting enter, and then I'm going to divide by negative 32. If you have a TI-34, you could also press that N over D button and do it all in one step if you wanted to do it that way. Okay, this way that I'm showing works with every type of calculator. And so now we get to a point where we've got one of the t-intercepts. So I get negative 2.3. I'm going to round it to 3 decimal places. I know it doesn't tell us in the problem, but in your homework it should tell you. And then the second one, I'm going to do negative 60 minus the square root of 18,320, enter, divided by negative 32. And I end up getting 6.105. Okay, so we get two t-intercepts, a negative one and a positive one. And remember that when we talked about plausible domain, we said we're really only concerned when time is positive, because a negative time, that does not make sense. So I'm going to cross that off, say it doesn't make sense. And I'm really just going to focus on this t-intercept right there. And so let's put this all together. I'm going to make a nicer graph. I know I kind of started to graph a little bit with my picture of my building, but I'm going to come down here and I'm going to put this all together with a graph. And so on my graph, I'm just going to label we'll call this t-axis and we'll call this d-axis. Now I know that the ball starts at 230 feet, so maybe I make this, I don't know, we'll say this is 100, I'll go up by 25, so 50, 100, 25, 50, 75, we'll say this is 200, 225, 250, okay, so we've got enough values there to represent 230. And then our time, I know I want to include 6 there, so it's up to you. 1, 2, 3, 4. I'm going to make each of these boxes just 1 second. 3, 4, 5, 6. I contemplated making them half a second, but then I noticed I wouldn't have enough room, so I'm just going to make each box 1 second. And so now let's plot what we know. So we know that the t-intercept is 6.105, so a little bit more than 6. That's the t-intercept, which is right here. We know that the d-intercept, the y-intercept, or where the ball starts, is 230. So 250 is right there. There's 225, looks like about right there. And so we know that it's going to go up and peak. We're going to graph the vertex. So I'm going to go up top here. We're going to find the vertex again. So the vertex is 1.875, and I'm going to write it down here. 286.25. Okay, so you know what I'm noticing here is the way I label my axis, my d-axis, I'm not going to actually be able to fit the vertex. So you know what, let's do this. I'm going to just redo this real quick, real life math here. And so what I'll do is I'll make each of these 50. So I'll go up, we'll say this is 50, this is 100, this is 150, 200, 250, 300. Okay, little squish, but that's okay. At least it all fits. So now I can graph this is my d-axis. So the ball starts at 230, so we'll put it maybe about there. And then the peak happens at about 1.875 seconds, so maybe like right here, and at 286. So maybe like right there. So this is my vertex. So the ball is going to go up, It's going to peak, and then it's going to go down. So it looks like a pretty wide parabola. So you can imagine the parabola does, if we just graph it mathematically, forget about the bowling ball for a second, the parabola does have another side to it, but this side doesn't really make sense for the problem. We don't really care about that negative side because we just are concerned about the bowling ball. So really we're just concerned about from right here to right here when it's released and then when it hits the ground. And then h, how would we use the graph to estimate the value of h of 3 and what does it mean? So let's do that. So how will we use the graph to estimate the value of h of 3? So that's the height when time is 3 seconds. So what I could do is I could come to 3 seconds and I could go up to the graph and see about what point that 3 seconds would hit the graph, and it looks like it's about right there. And just judging by the graph, it looks like it's a little bit over 250. It's not quite as high as the Vertex, but just eyeballing it, it looks like it's a little bit more than 250, but we could also use the equation. So if we use the equation, we could plug 3 into the equation. So we could find h of 3 by doing negative 16 times 3 squared plus 60 times 3 plus 230. And I could just throw that all in my calculator. Plus 60 times 3 plus 230. And so I throw that all in my calculator and I get a height, so h of 3 equals 266. So it means after 3 seconds, the ball was 266 feet in the air. And if you look at like our graph, that was our estimation. I said, yeah, it looks like it's a little bit, it's above 250, but it's not as high as 286.25. So 266, there's our exact answer. And then just real quick, just to show you, you can always use Desmos. So remember, Desmos is a really good tool. Desmos.com, you just hit start graphing, and then you can put in your equation. So remember, it doesn't have function notation, so you just have to use y. So you'll do negative with the subtraction sign. They don't have a different negative sign. So negative 16x squared, so you have to only use x's and y's, and then plus 60x plus 230. Okay, and then we could just zoom out. And okay, so it's kind of hard to see. Sorry if I'm making you dizzy here. You know, you can, play with the zoom. Now the nice thing is you can take your mouse and you can easily find the vertex. So that just confirms. So algebraically, if you're doing these problems, finding the vertex, use Desmos to do a quick check, and then we ended up thinking that the y-intercept was 230. Well, if we come down here, we can see, oh yeah, the y-intercept is 230. We can also come down, I'm just dragging this with my mouse, we can come down to the x-axis and just double check that the x-intercept is 6.105. We can even check this one, which is that negative 2.355 value. We also got that. We just crossed it off because it didn't make sense, but this is a really great tool. We just checked and just made sure that all of our answers look correct.